shows a car driving along a nearly vertical banked racetrack. The angle is so extreme that without the correct physical conditions, gravity would pull the vehicle straight down the wall. To maintain this path, the car requires an inward pull directed toward the center of the turn. We call this a centripetal force. This is a functional classification, a job title, assigned to the net sum of real, existing forces like friction, tension, or normal force whenever they point toward the center of a circular path. In a conical pendulum, a bob swings in a horizontal circle. Only two primary forces act on the mass, gravity pulling vertically downward, and tension pulling diagonally up the string. We can resolve the tension vector into two parts. The vertical component, T cosine theta, acts directly against gravity. Because these forces are equal, the bob stays at a constant height. The horizontal component, T sine theta, is the only force left. Because it points directly toward the center of the circle, it fulfills the role of centripetal force, constantly changing the bob's direction. By dividing the equations for these two components, we can solve for velocity and the time required for one revolution. This derivation proves that horizontal circular motion is simply the result of balancing vertical and horizontal force vectors. Consider a car on a banked road under frictionless conditions. The normal force, the push from the road, is perpendicular to the tilted surface. Just like tension in our pendulum, this normal force resolves into vertical and horizontal components. Without friction to help, the horizontal component of the normal force is the only factor turning the car. This geometry dictates one specific speed where the car will neither slide up nor down the bank, the square root of rg tan beta. If the car speeds up past that baseline, it tends to skid outward and up the bank. To stop this, static friction engages, pointing downward along the slope to pull the car back into the turn. This downward friction vector provides an extra inward pull. By resolving friction into its components and adding them to the inward normal force, we calculate the maximum safe speed the car can handle before losing its grip. Now, imagine the car slows down significantly below the baseline speed. In which direction must the friction vector point to keep the car from sliding down into the center of the track? At low speeds, gravity dominates, so friction must point up the slope to hold the car in place. Friction acts as a directional safety net, turning a single safe speed into a wide range of operational velocities. Vertical circular motion is different because speed changes as gravity pulls against the rise or accelerates the fall. We can see the impact of this by comparing a flexible string to a rigid rod. For a ball on a string to reach the top, it must maintain enough speed so the string doesn't go slack. At the highest point, the minimum speed is the square root of gr. To have that much energy left after climbing the full diameter, the ball must start at the bottom with a speed of at least the square root of 5 gr. A rigid rod provides structural support and cannot go slack. This allows the velocity at the top to drop all the way to zero without the ball falling inward. Because it doesn't need that extra kinetic energy at the peak, the required starting speed at the bottom drops to the square root of 4 gr. Let's apply this to a specific problem. A ball on a string starts at the bottom with a velocity of root 5 gr. We need to find the tension in the string when the ball reaches the horizontal 90-degree position. First, we apply energy conservation. The ball starts with 2.5 mgr of kinetic energy. By the time it reaches the horizontal mark, it has climbed a height of r, converting 1 mgr into potential energy. This leaves 1.5 mgr of kinetic energy, meaning the velocity squared is now 3 gr. Next, we find the required centripetal force for this new velocity. Plugging 3 gr into the force equation gives us a required inward pull of 3 mg. At this horizontal position, gravity pulls straight down and contributes nothing to the inward centripetal force. Therefore, the tension in the string must provide that entire 3 mg pull by itself. This summary highlights the three mechanical systems we've explored. While the scenarios change, the underlying method of resolving forces remains constant. By identifying how forces resolve and energy shifts, you can predict the behavior of any system in circular motion. Whether it's a pendulum or a banked racetrack, the physics is a matter of clear vector analysis.